Okay, so in the last class we saw a couple of algorithms for minimization, unconstrained minimization of a unimodal function, right? Effectively, the only requirements that we needed was that there's a well-defined minimum, and to the left of the minimum the function is strictly decreasing, and to the right of the minimum the function is strictly increasing. That is the only uh, assumption that we made on the function that we wanted to minimize. Of course, we also want an interval a0 to b0 where we know for sure that the minimum lies, right? And the algorithms that we saw essentially iteratively try to reduce the search space by a constant factor every time. And we saw that the size of the search space typically decays exponentially in the number of iterations that we run the algorithms for, right? So that's a very useful property to have. So we saw two algorithms. The first was this golden section search, or the golden section method. And the second algorithm that we saw was the bisection method. Now, the bisection method can be applied only if you have access to a first order oracle, that is, a function is differentiable and you can compute the derivative at every point within this interval a0 to b0. All right? All right, please settle down. Any questions? All right. So all of this assume that we have access to some interval a0 to b0 where we know for sure that the minimum lies. What if we don't have this? One way is to, as I said previously, use the bracketing approach, try to find an a, b, c such that f of c is less, if c is strictly between a and b, and you can find, so you have some a, b, c such that a is less than c less than b, and f of c is below f of a and f of b. And if you can find this, then you can go ahead and use your favorite search technique. But even this requires some approach, right? You need to have some way of finding such an a comma b. What if we don't have this? And is there an alternate approach which does not, which essentially doesn't work on reducing a search space, because it means that you already have some finite interval to begin with, right? So one approach that we'll see are these class of gradient based methods, right? Or in the context of one dimensional optimization, derivative based methods. So you need the function to be sufficiently smooth, and if so, then you have a bunch of different techniques for minimizing this function, even if you cannot locate an a0 comma b0. Okay. All right. So the first technique is something that you're all quite familiar with, just gradient descent, right? In the context of one-dimensional optimization. Right? How does this algorithm work? You start with an arbitrary initial point. Okay. So we start with some x naught. Let me denote this x of 0. All right, and you fix some step size delta t. We'll see how one can possibly choose this delta t later. So delta t for t equal to 1, 2, 3, and so on. You could fix a delta t equal to delta for all t. That's one way of choosing the step size, but there could be other ways also. Okay, and you iteratively run the following. So x of t is equal to x of t minus 1 minus delta t df of x t minus 1 by dx. Right, that's the standard gradient descent, and you keep running this for until convergence. Okay, so that's one particular approach. This does not require you to know where the minimum could lie, but potentially you may have to go through a huge number of steps in order to reach the minimum. Okay, we'll see a different approach which makes use of both the first and the second order derivatives. And that is something that will be useful even when we talk about minimizing functions over Rm, not just over R. Okay, so we're given f from R to R, and we assume that f prime and f double prime exist.
So the gradient descent only existence of the derivative is.
That's sufficient. In fact, you don't. Okay, since if we assume that the function is convex, we don't even need the existence of the gradient or the derivative. You might as well use the subgradient and go ahead. That's the power of the gradient descent method. Even if the function is not smooth, you can still use the gradient descent approach. I'll talk about it when I talk about functions over Rn, but essentially you do not require the gradient to exist, because you know that the subgradient exists at every point. We've seen that previously. As long as the function is convex, for every point in the domain, the subgradient exists. And instead of using the gradient over here, you might as well just replace it with the subgradient. It'll work. I mean, it's a valid algorithm. How fast it will converge, no guarantees.
But you have to be careful to fix delta low.
You have to be careful.
To fix delta low.
You have to be careful with delta. So I'll talk more about delta a little later. Okay, but as long as you have some guarantees on f, and of course delta is kept fixed, you can prove that x gets very close to x star, the local minimizer, or the global minimizer in this case.
Can you give a bound for delta so that it guarantees convergence?
So in fact, we'll see. I'll talk more about it a little later when I talk about gradient descent in full generality. I'm sorry?
Work on lambda max. The lambda is the eigenvalue of the function.
What do you mean by eigenvalue of a function?
Because like I don't know exactly, but it is it might be the eigenvalue of the Hessian, not too sure. But it is still for lambda max somewhere I saw.
Well, it depends. I'm not sure which particular result and what they are talking about and what assumptions that requires, but we'll see how close we can make f of xt to the minimum, the minimum f star within a certain number of steps. So we'll do a more detailed analysis of gradient descent in a little bit, but for now we just see the high level intuition behind these approaches. And in practice, you typically don't choose delta to be a constant. There are other ways of choosing delta t. And that's the whole point of this discussion that we'll go through next. Okay. So the main, moving to Newton's method, the main idea behind the Newton's method is, so one can view the gradient descent approach as sort of taking a first order approximation of the function at each step and then trying to take one step in the direction of the first order approximation. So what is a first order approximation of a function? It's just a straight line, right? So you take this straight line and you move in the direction where the straight line is going downwards. And you do this at each step. Okay, that's sort of the way to think about gradient descent. So you have this function, you start with a random initial point. At each step, you can look at the first order approximation of this particular function, which is nothing but the tangent, right? That's what gradient descent is all about. So you take the tangent at this particular point and you move a certain distance in that particular direction. All right, so this is your whatever delta t times the derivative. Correct? So you move in that particular direction. This gives you another. So this is your x0. This corresponds to you start with x0, take the sort of first order approximation, which is just which corresponds to the tangent at that particular point. You know that in the direction to the right, the function is decreasing, so you take one step in that particular direction, and the amount you move in that direction is just delta t times the derivative at this particular point, and you get some x1. And at this particular point, now you again construct the tangent, which is the first order approximation. And you get another x2. You move along this direction, you get maybe an x2. And once again, you construct the first order approximation to get x3 and so on. And so on and so forth, right? You move back and forth until you hopefully eventually get to the global minimum. Okay. Newton's method, on the other hand, is you can think of it as another generalization of this gradient descent approach. Instead of looking at the first order approximation to the function, you look at the second order approximation to the function. All right. So basically, you approximate f by a quadratic function. And how do you do that? Just take the first two terms in the Taylor series expansion. So suppose I have some particular xt. How do I get xt plus 1? I try to minimize the second order approximation to f at xt. So let's define gt of x to be f of xt plus the derivative of f at xt times x minus xt plus f double prime xt by 2 xt the whole square. So the right hand side is a quadratic function. Is this always guaranteed to have a minimum? A unique global minimum?
Second derivative is greater than 0. Then
Sorry? Yeah. Can you?
F is convex, F double prime is positive.
Right. So as long as f double prime of xt is greater than 0, greater than or equal to 0, this is guaranteed to have. In fact, you need f double prime of xt to be strictly greater than 0 to have a well-defined global minimum. All right. If f double prime of xt is equal to 0, then you just get a linear function, and then the minimum will be at either plus infinity or minus infinity. All right. So the main requirement here is that the function be convex. If f is convex, then f double prime xt is greater than 0, or at least greater than or equal to 0, and then you can hope to minimize the right hand side. All right. In fact, we will require f double prime to be strictly greater than 0. So what is the minimum equal to? Or how do you find the minimum? How do you minimize the function? The right hand side is a convex function. So we've seen some necessary and sufficient conditions for a point to be a minimum. What are they? Yeah? It's just a function over R, right? So the derivative should be equal to 0. So you just use the first order necessary condition, which also happens to be sufficient for convex functions. So you set gt prime of x to be equal to 0. And what does that give us? Right, or my x t plus 1 is going to be equal to x t minus the derivative of f at xt divided by the second derivative of f at xt. Any questions? So yeah, so gt, I don't say that gt is equal to f of x. Right? gt is equal to f of x only if the function is a quadratic. We're just approximating f by the second order Taylor series expansion. So gt is exactly the second order Taylor series expansion of f. Okay? We just take the first three terms in the Taylor series expansion and stop at that. Okay. Again, it's a heuristic algorithm, right? Questions? So there's a lot of similarity between this and the standard gradient descent algorithm that we've seen previously, right? You can think of this 1 by f double prime of xt to be like your delta t. You can view this in some sense as a step size. But of course, yeah.
Why does minimizing GFT mean we're minimizing everything?
I'm not saying that we're minimizing f of x at all, right? The only thing that we're guaranteed here is that at every step you're always moving along the right direction. In every step you're moving along the direction of the minimum, because the direction that the Newton algorithm takes is the same as the direction that the gradient descent algorithm takes, because f double prime of x is guaranteed to be greater than 0 for every x. It's a convex function. So in every step you are moving along the direction of the steepest gradient, right, or the steepest descent.
Can you also look at this as every time you are approximating it as a quadratic
Correct.
and finding the minimum of that particular quadratic?
Correct. Exactly. That's exactly what you're doing. All right. So again, if you think about it, let's say you have some sort of a function. I'm sorry? Correct. Has 3 terms, correct.
When we take the derivative, we ignore the last part, the last term,
Which last term?
f double dash of xt,
Correct.
and it's d1, x minus xt whole square.
Yes.
I will not take the derivative with respect to this.
You did. We did, right? So this is what you get. When you take the derivative, the first term it's a constant, right? This doesn't depend on x. Xt is, so we're expanding we're using the Taylor series expansion about the point xt to get xt plus 1. All right, so you still have both of these terms, the second and the third term appear. So one way of thinking about this is at each step, so you have some weird convex function. At each step, you look at the quadratic. So let's say I'm at this particular point. I approximate the function by a quadratic that passes through this particular point and has the same first and second derivatives as right. So the light blue curve essentially corresponds to the quadratic, which has the same first and second derivatives as this function f. All right, the first derivative and the second derivative of f and the first derivative and the second derivative of this g naught are the same at this particular point here. Okay, you minimize g naught and to get some particular so this happens to be the minimum of this particular quadratic function. So you take this as your second point. You repeat the same. You look at the quadratic that passes through this point and has the same first and second derivatives as f at that particular point. So that gives you something else. Maybe this is the quadratic. Again, you try to minimize it, you get another point, and so on and so forth. Okay. Now, the face of it may not seem like we're doing anything much better than the gradient descent, right? Except that we're using You can think of it as taking a different step size every time. But we'll see some examples later in higher dimensions. But one advantage that Newton's method offers is that if the slope is not, so if the derivative is high, then, I mean, if you think about it, the derivative is very large, then the approximation, the second order Taylor series approximation, is going to look like a quadratic which is very sharp. All right. On the other hand, if the second derivative is sort of, or if the first derivative is large, so basically if you take a point over here, then the second order Taylor series approximation is going to look something like this. All right. What this means is that if you're at a point like this where the function is decreasing or increasing gradually, what Newton's method does is that it takes a larger step. All right. So at these points, Newton's method will take a larger step, whereas at these points over here, Newton's method will take a smaller step, because it's expected that if it's very steep, then you're somewhere close to the minimum. But on the other hand, if the function is only gradually decreasing or increasing, then potentially the minimum could be much further away. All right. Again, it's a very high level intuition behind Newton's method. It doesn't mean that it's guaranteed to, because the third and fourth order derivatives could be very weird. It could change the landscape of the function entirely. All right. But in many cases, Newton's method can converge much faster than gradient descent. Of course, it requires you to be able to compute the second derivative.
Is the function strictly convex? Can we say that it will always guarantee convex?
So we do require it to be strictly convex because we want f double prime to be strictly greater than 0. Otherwise, this doesn't even make sense.
Then you could have part of it that's strictly convex and the other part that isn't.
Then what happens here? How do you define xt plus 1?
Yeah, at some point you can't define, which is why.
Correct. So that's a fundamental requirement behind. Then it's not Newton's method. That's it. You could define an algorithm that is like Newton's method, but not exactly. Okay. Any questions?
Is f reducing at every iteration? Can you show?
F is, in fact, it will reduce at every iteration. By how much? Again, that depends on the value of f. That depends on the function f. But in this case, the function is strictly convex, and you're taking a step in the direction of steepest descent. So it must mean that the function value is decreasing at every step. You can't say so in the case of gradient descent, because it could be that you took a step too much. So, for instance, you could be running gradient descent. Let's say you're at this point and you take a step that was too large, the function value could potentially increase. All right, if your step size is too large.
Newton's method will never overstep.
Newton's method kind of will not, intuitively it will not overstep.
So, this problem is there even if it's a convex function.
Which one?
With the gradient descent.
Yes, of course. Because if you choose your delta to be too large, then
Because of the delta.
because of delta.
Because f has kind of got some nice properties. in it.
That is true. Yes,
F prime.
correct.
Can we prove that it won't overstep?
In which case? In Newton's method? You can prove that it will not overstep. Although I don't know of a proof right away that I can give you. Okay. Any other questions?
What exactly is G?
So G is just a quadratic approximation of the function f.
So F can be any function.
F can be any convex function, any strictly convex function.
We are approximating at that point.
At that point, you are approximating by a quadratic function. So at each step, this is your x0, right? So you approximate the function f by a quadratic about this x0, minimize that, you get x1. So this is your x1, right? So this is your x1, and then you approximate this by another quadratic about x1. You minimize this to get x2, and then you keep repeating the same thing.
So x0 is already decided for any function.
X0 is typically chosen randomly. All right. In most of these algorithms, you need some way of choosing an x0, and you can give guarantees only if x0 is not too far away from the global minimizer. Of course, if it is too far away, then it will take a very long time to converge, which is expected of any such algorithm. All right. But typically you just choose it randomly according to some distribution. All right. Or if you have some other way of approximately knowing where the minimizer could lie, then you start with that as the initial point. Typically in many optimization algorithms, one way is, of course, you choose it completely at random, which is sometimes called a cold start. Another way is to first run a less complex but maybe poor optimization algorithm to get something that is not too far away from the minimum, and then use this as the initial point for a better minimizing algorithm. That's what is called a warm start. All right. So there are a number of ways of speeding up finding minimizers of like optimization problems. Okay. Okay. So all of this discussion was for functions on R. Our end goal is, of course, to design optimization algorithms for functions over Rn, or at least some vector space. Right? And the class of algorithms that we look at for solving multivariate optimization problems are essentially these descent-based approaches. All right, so now we'll assume that f is convex. And we are going to look at unconstrained minimization of a convex function f. So most of these algorithms, these are these descent-based approaches. So we'd use all the algorithms that we look at take the form x of t or x of t plus 1 is equal to x of t minus some or plus some delta t times a direction vt. So this is the direction. And this is the step size. So first, how do we choose the direction? If the function is convex, then what is the best direction to choose? the direction, you should choose the direction which is the negative of the gradient. Because as we've seen in assignment 1, that is the direction along which the directional derivative is the minimum. Right? That's the direction of the steepest descent. So we choose Vt to be the negative of the gradient of f at xt. That is if the function is differentiable. If not, you just choose any subgradient. Now mind you, the subgradient is not unique if the function is not differentiable at that particular point. So how do you choose the subgradient? We just fix a rule. Okay, whatever is easiest to find. So you just fix a rule, how we are going to choose the subgradient at each point. Because there could be multiple subgradients. Right? Okay, so the direction that we should move along is kind of fixed. How do you choose the step size? So one way is to keep a fixed step size. That's what you've seen in assignment 1, and that's the most common way of sort of also, we'll also analyze gradient descent with just constant step sizes. So choose delta t to be equal to delta, some fixed delta for all t. But as we've seen in assignment 1, choosing a constant step size can potentially make you overshoot and could be detrimental to convergence. All right. So what is the other approach? Well, one other approach is to choose a delta t that depends on t. Maybe initially you take larger steps, and then later on you keep decreasing the step size. So you choose delta t that depends on t. Maybe delta t is equal to, say, some delta divided by t plus 1, perhaps. Okay, some decreasing function of t. So that eventually you're guaranteed to get closer and closer to the minimum. The other approach is, now in these two cases you are fixing delta t beforehand, irrespective of which point you are at. There's another approach where you choose delta t depending on where you are. For example, that's what Newton's method would do, right? But Newton's method requires you to know the second derivative. But even if you know only the first derivative, there are other approaches you can use. So what you can do is you can search for the best delta t. All right. I'm sorry?
What is search delta?
I'll elaborate on that just a little bit. So there are different ways of searching. All right. So one thing is, once you fix a particular direction, all right, let's look at the function. So you fix the direction v, you're sitting at a point x. What you can do is look at the function f along the direction v starting from the point x. Okay, so phi v of, let me call it alpha, this is f of x plus alpha times v. Okay, so I look at this function phi v of alpha. If f is convex, then what can I say about phi v of alpha? Yeah?
Convex is
It's guaranteed to be convex, as we've seen. So what I can do is now, at each step, I can try to solve a one-dimensional minimization problem. Right? We've already seen different algorithms for doing one-dimensional minimization. I could use either the bisection rule or if I have the derivative at every point, I could just use the bisection method, or I could use the golden section method. I could just use that to at every step I try to minimize this function phi v of alpha, which hopefully gets me closer to the minimum faster using fewer number of steps. But there is a caveat. What is that? Yeah? Okay, A naught and B naught, true. What else? Let's think about the complexity that is involved. Look, the overall running time, I'm counting the overall running time based on the number of oracle accesses that I have to make. That is the number of times I evaluate f or gradient of f. Okay, I'm saying that at each step I am reducing the problem from a multi-dimensional optimization problem to a one-dimensional optimization problem, and then trying to do this one-dimensional optimization problem in each step. But I'm hiding something.
The granularity with which you move V.
Not really. Again, everything is in the context of complexity. What do I need to do in order to solve this one-dimensional optimization problem?
Distinct directions.
What kind of an oracle do I have to access at every step to solve this one-dimensional optimization problem? Depends. Okay, zeroth order or first order oracle, which is in what dimension? N. All right. I have to access the n-dimensional first order or the zeroth order oracle, right? Because ultimately, this is what I compute, right? At every step, I have to compute this function. It is a one-dimensional optimization problem, agreed. But at every step, I have to compute this n-dimensional, this function over n dimensions. All right. So I'm not really getting too much reduction in the complexity. But the only advantage is, hopefully, compared to say gradient descent, I could be taking potentially I could be taking longer steps. Right, and which will eventually let me converge faster. Okay, so that's one particular approach, but we have to be careful when we talk about complexity, because complexity not just includes computing this. The complexity will involve not just computing this direction v, but also computing delta t, because that has an added complexity for use search algorithm of this particular form. So I can use whatever, the golden section, or the bisection method. Okay. But in practice, typically you don't use something like golden section or bisection method because it's too computationally intensive. You don't want to find the exact. So both of these approaches effectively try to solve the optimization problem exactly, right? Which may be too much, because anyway, that's not the direction of the true minimum. It is somewhere along the direction of the minimum. It's only when you move in the direction of the negative gradient, it only means that the function decreases in that direction. It doesn't necessarily mean that the minimum is exactly along that particular direction. All right. So it may be too computationally intensive to find the minimum at every step. All right. So what else can you do? Well, you can try to do something approximate. Instead of trying to minimize the function phi v, instead of trying to minimize this, you try to move along that direction just so that the function value decreases a sufficient amount. Okay, so there's one popular approach which is called the backtracking method. Right, or the backtracking line search. So what you do is, again, you look at this function phi v of alpha, and you choose phi v of alpha such that, so you choose an alpha such that phi v of alpha minus phi v of 0 is less than or equal to alpha times some constant that is fixed beforehand, times the derivative of phi v at 0. So remember that phi v of 0 so this is nothing but f of xt, this is f of xt plus alpha v, and this is derivative of gradient of f of xt inner product with v. Right. So basically what this is saying is that, look, at xt, this is the value of the function. If you move, hopefully you've chosen the direction where the function decreases, right, which is hopefully along the direction of the negative gradient, then this phi v of alpha will be less than phi v of 0. Okay, because you're moving in the direction. So if v is the direction of steepest descent, then if alpha is positive, then f of x plus alpha v will be hopefully less than f of x. Right? So this quantity is going to be negative as long as alpha is not too large. Of course, the function could decrease and then increase, but up to some value of alpha, this whole quantity is going to be negative. Okay? And how far do you go in the direction of v? Well, we just set a baseline. We say that it should be less than alpha times c times the derivative. Okay. As of now, it's kind of a heuristic rule. Okay. But in practice, this turns out to have the best trade-off between computational complexity and speed of convergence. That is, you don't make too many oracle accesses, but at the same time, it does much better than choosing the step sizes beforehand. And this is one of the most popular ways to choose the step size. So that's something that's fixed beforehand. The rate of convergence, of course, depends on C. But if C is large, so basically this phi v of 0 is something that is negative, because let's say you're moving in the direction of descent. So this quantity will be negative, this quantity is positive. So a larger C means that you take a larger step, but potentially you may have to make a lot of oracle accesses. I haven't still told you how do you choose your alpha. I said that you choose an alpha such that this happens. And this itself involves a search. All right? And how do you do this? So basically you fix an alpha naught. Okay.
How did you differentiate 5?
How to differentiate phi v? So phi v is the function along this direction, right? So how do you find the derivative of phi v? You just use the chain rule. So this is a composition of a function from R to Rn along with a function from Rn to R. Alright? So what does the chain rule tell you? It's equal to the derivative at this particular point, the gradient, so phi v prime of any alpha, right? This is equal to, by the chain rule, the gradient of f evaluated at x plus alpha times v times the derivative of x plus alpha times v, which is this. Right? So in fact, to be more precise, this is equal to the derivative of f at x plus alpha times v times v, which is the derivative of x plus alpha v with respect to alpha. But the derivative is nothing but the transpose of the gradient. So this is equal to the inner product between the gradient of f at x plus alpha times v along with v. So phi v prime of 0 is just the gradient of f at x transpose times v. Alright. Okay, so these are sort of commonly used search methods. So you have a higher dimensional optimization problem, you try to, at every step, you convert it to a one-dimensional search problem and try to solve that one-dimensional search every time. But then you can also, just as we use this particular approach, you can also use Newton's method for the higher dimensional problem itself. So this requires you to know not just the function and the gradient, but also the Hessian. All right, and just as in the one-dimensional case, at every step you find this gt of x. So gt is a function from Rn to R and is the second order Taylor series approximation of f at xt. F of xt plus the gradient of f at xt xt plus x minus xt transpose the Hessian times x minus xt. That's right. There should be half. Correct. So exactly as we did in the one-dimensional case, at every step we can try to minimize this quadratic. Again, we just use the first order necessary condition. This quadratic is guaranteed to be convex as long as the Hessian is non-negative. Right? In fact, we'll want more than that. The Hessian should be positive definite. And we'll see another reason as to why we want it to be positive definite and not just positive semi-definite. So GT, so we set gradient of GT of x to be equal to 0, which is same as saying that gradient f of xt plus Hessian f of xt times x minus xt, this is equal to 0. So x minus xt is equal to, let me do it step by step. F of xt, so x is, or xt plus 1 is equal to xt minus the inverse of the Hessian times the gradient. Right? Remember that in the one-dimensional case we had the derivative xt minus the derivative divided by the second derivative. But now the second derivative is not a number, it's a matrix. The Hessian is a matrix, so you have this matrix inverse times the gradient. This is only possible if the Hessian is invertible. Alright? We know the Hessian is positive semi-definite. What if one of the eigenvalues of this matrix is 0? It is not invertible. So we want all of the eigenvalues to be strictly greater than 0. Alright? So in order to use Newton's method, we need strong conditions on F. The Hessian should exist, but that's not enough. We want the Hessian to be positive definite, so it has to be strictly convex. Okay? If it's not strictly convex, then you can't use Newton's method. Any questions? Okay, let's maybe visually see how these two algorithms, the gradient descent and Newton's method, behaves for maybe an example function. Right, so I have this function f, which is basically x minus 1 the whole square plus, or let me perhaps write it out. So my f of x is, say, x1 minus 1 the whole square plus x2 minus 1 whole to the power 4. Okay. Is this convex? If so, why? I'm sorry? F double prime, again it's a function in two variables, right? x1, x2. Okay, do you want to really compute the Hessian? Is there an easy way of seeing that this function is sum of two convex functions is a convex function, exactly. And what about each of these functions individually? This is convex. This is also convex. Function. I'm sorry? That doesn't matter, right? No, minimum doesn't matter where it is. And again, it's not at the same point because this is a function of x1, this is a function of x2. Right? It's just the point that this is a convex function of x1, x2 because it's independent of x2. This is a convex function of x1, x2 which is independent of x1. The sum of two convex functions is a convex function. That's it. Right? Okay, you can compute the gradient and the Hessian in this particular case. The gradient is just this, right? It's 2 times x0 minus 1 or x1 minus 1 and 4 times x2 minus 1 the whole cube. Or if I have x0 and x1, then it's 2 x0 minus 1 and 4 x1 minus 1 the whole cube. So let's suppose that I run the gradient descent algorithm for, let's say, a certain number of steps, let's say 7 steps, starting from a random initial point. So basically what I've done is I've defined functions to compute the function value as well as the gradient. And I start with a random point. All right, that's my random initial point. And in gradient descent, my xt plus 1 is just xt minus some delta times the gradient. I'm fixing a constant step size over here. Okay? And that's it. I keep running this for how many ever iterations I want. So this is what it looks like. Hopefully you can see it. So I started with this initial point somewhere over here, and then I kept moving along the direction of the negative gradient. All right. Remember that the length of the step that you take is not delta, it is delta times the directional derivative. Okay, so the directional derivative is small, then you take a smaller step. If the directional derivative is large, then you take a larger step. Okay, so I did this for how many steps was it again? This is for 7 steps. Let me run it for 10 steps. Okay, so the actual minimum is that particular point up there, right? The one marked with a star. So the derivative is pretty small. The gradient is really small around this because of the x to the 4, right? And that is why it's really slowing down the whole process of gradient descent. So you need a really large number of steps in order to get to the minimum. I've increased this from 1 point, from 10 to 30 number of steps. If I run this for, it's 130 steps. Again, this also depends on where I start from. Right? But in general, you need a really large number of steps to get to the minimum. Okay, again, the main problem here is that the derivative is pretty small. Okay, on the other hand, if I have second order information, if I can compute the Hessian, then I can just run Newton's method. All right, so I can compute the gradient and the Hessian over here, and let me run Newton's method. And gradient descent with constant step size. All right, the trajectory of Newton's method, I'll just denote it in green, whereas the gradient descent, I'm just going to denote it in magenta. All right, so maybe this is too many steps. Let me fix the number of steps to, say, 7. So 7 steps of gradient descent versus 7 steps of Newton's method. Okay, so maybe a bad thing. You can't really visualize much. Yeah. So basically, you see that gradient descent, it still doesn't get you close to the minimum, but not bad. It has made some progress compared to what we saw earlier, because the initial points in these cases had turned out to be really good. But Newton's method converges much faster. All right. In fact, let me start with something worse. Okay, so let me fix x0 to be just the 0 vector. So all right. So the magenta trajectory is that of gradient descent. Green is that of Newton's method. All right. The one thing to note is that you see that after the first step, Newton's method is kind of moving vertically every time. I'm not sure if you noticed this earlier.
One question. Why would the initial directions different?
Why is the?
Why would the initial directions different? You do.
The initial directions are different because it's not. Let me perhaps go back to this here, right? Right, so this is Newton's method, whereas gradient descent is xt plus 1 is equal to xt minus some delta times f of xt, right? In this case, in Newton's method, I have this multiplication by this matrix. It's an inverse matrix. It not just scales the gradient, but it also rotates it. Right? So the directions that Newton's method and gradient descent take could be different. That's something that's very important to note.
Is Newton's method doing better here because this is like a quadratic light function?
Exactly, it is. In fact, that's the point that I was trying to make. So even if I start from a random initial point, right? In the first step, it takes a really long jump, and after that point, it moves vertically. Right? I can run it again. Initial point is different, but the same thing happens. Run it again, same thing, right?
So the quadratic part is
It's
done.
because the quadratic part is done initially, right? Because it's a sum of a quadratic and a quartic. It just minimizes the quadratic part immediately and then just goes ahead and tries to minimize the quartic. Right? So this is a nice function, and therefore you can see In fact, you can see how much faster Newton's method is compared to gradient descent. All right. If the actual function was quadratic in the first place, then it would just get to the minimum in one step. It wouldn't even take time. All right. Okay. Any questions? All right. So let's go back.
So it goes to the minimum on the quadratic slice first, so to speak.
No.
Okay.
It's not, right? It's making an incline. Right? But it minimizes the quadratic part immediately. Right? So what I want to do next, for which I will not have enough time for, is try to analyze gradient descent or the running time of gradient descent. All right? But we can't minimize, or you can't really analyze gradient descent without making certain assumptions on the function f. Because what can happen is, suppose you start from a point that is too far away from the minimum, you can't give any guarantees. If the gradient is, say, is too small or too large, again you can't give any guarantee. So you need some regularity conditions to understand the running time, and the running time will depend on each of these parameters. All right. So what we want to do is, we'll begin with some assumptions. So I'll assume that the step size is fixed. Delta t equal to delta for all t. And some assumptions that we'll require is, you start with a point that is not too far away from the actual minimum. Right, so x0 is, if x star is the is the global minimizer, then I will want that this is less than or equal to some b, some number b. The running time depends on this number b. Whether you know or don't know, it doesn't matter, but the running time depends on how far you are away from the actual minimum. Obviously, if b is large, it will take you longer to reach the minimum. The second assumption that we'll require is that the gradient is bounded. This is less than or equal to some rho for all x.
So what is the first assumption? Like, isn't it always
Which one?
the first?
The first assumption, it basically tells you that, you can think of it as a parameter.
But like, isn't it always true?
I know, but then how long you take to converge to the minimum depends on b. All right. So if you want to choose an appropriate, in fact, we choose delta depending on b and rho. All right. So the choice of delta depends on b and rho, which means that you know these beforehand.
How would I know B, because I don't know X star in the first place?
You don't know x star, but again, it just has to be a bound. Maybe you know that the minimum lies within a ball of radius something 100. All right. And in fact, the second relaxation, it holds true even if you're running gradient descent not with the actual gradients themselves, but with subgradients. Okay. So what we want to know is in t steps, or in other words, I'll put it slightly differently. What we want is f of x to be less than or equal to so in t steps we want f of xt to be less than or equal to f of x star plus some epsilon. So we want to be epsilon close to the minimum in this sense. So earlier, at least in the search based methods, we were happy with just having x to be sufficiently close to x star. But now the condition that we'll analyze is a little bit different. It's in terms of the function itself. What is the function value? All right. So we want f of xt to be less than or equal to f of x star plus epsilon. We want to know how long do we have to wait? What is the value? What is the typical value of t for a given epsilon, b, and rho? All right. We'll see that under these assumptions, the gradient descent can converge, can satisfy this as long as t is greater than or equal to b square rho square divided by epsilon square. Right, so this tells you in t steps, or how many steps you have to take in order to get epsilon close to the minimum. This depends on b. It's quadratic in b, quadratic in rho, and quadratic in 1 over epsilon. All right, but there's a slight caveat here, and that is if we choose delta to depend on b, rho, and epsilon, that's something we have to do. And in fact, we choose delta to be equal to b divided by rho times square root of t. So you know beforehand how many steps you're going to take, in a sense, and you know b and you know rho. So under these assumptions, you can guarantee, this is the kind of guarantee that you can get using gradient descent. I don't say that this is the best, the tightest result that you can derive for the analysis of gradient descent. You can make other assumptions. So for instance, instead of assuming that the gradient is bounded, people can make other assumptions such as
So this delta is just strictly that not less than or equal to.
I'm sorry?
So delta should be strictly be
Yeah, if you choose this particular delta, you get this. We'll see. All right. So the other kind of assumption that one can make is, for example, that the gradient could be Lipschitz continuous. It's a standard assumption that people make, which basically says that if you take any 2 points, then the difference between the gradients at those 2 points is less than or equal to some constant times the distance between those 2 points. So the rate of convergence will depend on this parameter L. All right. And in fact, if you make these assumptions, then you can show that you can get the same sort of guarantee as long as t is greater than or equal to some constant times LB square divided by epsilon. So it's still quadratic in B, but now it's only linear in 1 over epsilon. So the dependence on epsilon is now improved just by this assumption. It's the same algorithm, right? It's exactly the same algorithm. It's just that the assumptions that you made changed. Okay, for a different class of functions, you have a different running, bound on the running.
So the previous assumption B.
Correct.
Second, you can never find such a row.
You can never find such a row. Why is that true?
always find a gradient that's larger than a gradient.
Correct. So for example, we'll assume that in this region, in fact, as we'll see, it's sufficient if in this entire region, this gradient is less than or equal to rho. It doesn't turn out, of course, just for the analysis we will do this, but it's not strictly required. All right. So all of these assumptions can be reduced to the case where, let's say, you're always within a ball of radius b around the minimizer. Delta is kept a constant. But I'll make a small tweak to the gradient descent algorithm, or how we choose the final xt. Okay, so maybe this is a good point to stop. Any questions?